Welcome to part 3 of the video podcast series on Chatellier's principle in equilibrium here at Ontario High School. We're going to talk now about the addition or removal of heat. In parts 1 and 2 we talked about what happens with changes in concentration and changes in pressure. So now time to do the heat. Just a definition of equilibrium. For you to read. I am not going to read it to you because I've read it to you twice. So if you feel like you need to spend some time with this, just pause the podcast and read that carefully and then move on to the next slide. Again, if you need to reread this, it's just statements that I have provided in previous podcasts. Go ahead and pause it if you need to read this carefully. It will certainly help you in any case. Those of you who have heard me for very long know that precision is very important to me, and it is the reason that I continue to quote authors Stephen S. and Susan A. Zumdahl from Chemistry 7th edition. If a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce that change. This is the key to understanding Le Chatelier's principle and being able to predict changes that will occur due to stresses added to an equilibrium system. Let's consider the addition or removal of heat. The equilibrium system based on the Haber process, which you have seen many times. N2 plus 3H2 yields 2NH3 plus 92 kilojoules. Now, this is really important to note. In a thermochemical equation, a heat value written on the product side represents an exothermic reaction. If we were just to write the delta H here, which is the change in enthalpy, in this case, we're just going to represent it with a Q. When written by itself, Q would equal negative 92 kilojoules. So when the heat value is written on the product side, if we write it separate from the chemical equation, we have to put a negative sign in front of it, representing that this is an exothermic reaction where heat is being given off by the system. Heat is being released to the surroundings. If this were an endothermic reaction, the heat would be written on the reactant side of the equation. And in the chemical equation, we don't include negative signs indicating that direction. Its direction is indicated by its position, whether it's written on the product side or the reactant side. Let's look at an application statement that will be very important for us. A change in temperature also constitutes a stress on the system. Unlike changes in the analytical amounts of reactants and products, a change in temperature produces a change in the equilibrium constant itself. An increase in temperature is the result of the flow of heat into the system. A flow of heat out of the system reduces the temperature. A reaction itself can be a source or sink for heat. The heat flow for a reaction is characterized by the enthalpy of reaction or the heat of reaction, delta H sub Rxn. Increasing the temperature of an exothermic system adds an influx of heat which pushes the system away from equilibrium. Equilibrium is restored by removing some of this additional heat. The reaction will favor the reverse reaction, a decrease in the products and an increase in the reactant concentrations will be observed. If the temperature of a system were decreased, heat removed from the system, the forward reaction would occur to release heat in an attempt to offset the heat that was removed from the system. Well, we're looking at the reaction of N2 with 3H2 forming ammonia and 92 kilojoules of heat. If we add heat to the system, how will the concentrations of the reactants and products be affected? So this is our sample problem. What I'd like you to do is pause the podcast and go ahead and answer the question, and when you're ready, resume the podcast and compare your answer to mine. Okay, let's take a look and see if your answer matches mine. We added heat to the system. It's an exothermic reaction, so adding heat is like adding a product that will shift the reaction to the left. So The effect on the concentrations of the reactants and products would be to increase the concentration of N2 and H2, which are reactants, and to decrease the concentration of our ammonia. How'd you do? Let's look at another problem. Consider the equilibrium system where we're adding heat to solid calcium carbonate and forming solid calcium oxide and carbon dioxide. Our K is equal to the concentration of CO2 because we do not include solids or pure liquids in equilibrium expressions. Our K sub P would be equal to the partial pressure of CO2. So how will the amount of CO2 be affected by the addition of heat? Would you go ahead and pause the podcast and make your prediction? After you've made your prediction, go ahead and resume the podcast and we'll see how your answer matches up. Alrighty, welcome back. Let's see how you did. Heat is a reactant in this, or it's on the reactant side, so we treat it like it's a reactant. We're adding heat, so it should shift the equilibrium to the right. So our amount of CO2 should increase. And if you look at this logically, we decompose calcium carbonate by heating it. So if we're adding heat, we should be producing more CO2. And in a closed container equilibrium situation, that's indeed what would be happening here. Well, another sample problem. Let's look again at the Haber process. N2 plus 3H2 yields 2NH3 plus 92 kilojoules of heat. If heat is removed from this system, how are the concentrations of the reactants and products affected? Pause the podcast, answer the question, then resume, and let's see how you did. Well, let's check your answer. If heat is removed from the system, how are the concentrations of the reactants affected? So your concentration of nitrogen and hydrogen are going to decrease because you're going to favor a shift in the equilibrium to the right since you're removing heat really as a product of the reaction. So your concentration of ammonia, NH3, should increase. Time for a your turn problem. You're probably thinking, but we've been doing those under the guise of sample problems. Yeah. Well, here's a your turn problem. Consider the following reaction that reaches equilibrium at 520 Kelvin. Here we have the synthesis of hydrogen iodide from hydrogen and iodine gases. And this is exothermic. It produces heat. So what will happen to the amounts of reactants and products if A, heat is removed, B, heat is added, and state as well whether the equilibrium shifts left, right, or is unchanged. Let's take a look and see how you did. If you remove heat from this reaction, it's as though you're removing a product of the reaction, so the equilibrium will shift to the right, the concentrations of hydrogen and iodine will decrease, and the concentration of hydrogen iodide, HI, will increase. If heat is added, it's like adding a product, and you would be shifting the reaction to the left. Your concentrations of hydrogen and iodine, H2 and I2, will increase. Your concentration of HI will decrease. So that is how that goes. I hope you did well with that. If not, review about Le Chatelier's principle in your textbook. Certainly rewatch the podcast. That will be helpful. There are many online chemistry tutorials from university websites that are very helpful with this as well. Well, this is the end of part 3 of the video podcast series having to do with applications of Le Chatelier's principle in equilibrium systems. I want to leave you with a quote from famous President Calvin Coolidge. "I have never been hurt by what I have not said. I wish you well."